This is the video for pre-lecture 14. In the past few lectures, we've looked to determine approximations for derivatives in terms of the value of the function at particular locations in the space. We can use these approximations then to solve for ordinary differential equations and then ultimately use those methods for solving partial differential equations. So we're going to start off by just looking at the simple, or in really a very simplified version of the heat equation. So the 1D heat equation is d phi dt is equal to kappa times d squared phi dx squared, where kappa is our diffusivity coefficient. If we make the approximation that our solution is steady state, though, this steady state approximation then allows us to assume that things are not changing with time, so that our d phi dt is equal to 0. Then our system reduces to just simply d squared phi dx squared is equal to 0, because we can divide both sides by our diffusivity coefficient kappa. Okay? So this is now the governing equation for the steady state heat equation. And so the question is, though, how can we solve for this for a particular system? Well, if we assume that we've been given a space that we've discretized using maybe 6 discrete points in space with 2 at the ends, we can say that, okay, we want to approximate our temperature profile with temperatures at each of these 6 points. And again, we have our boundaries at our 2 endpoints precisely. So if we discretize our system into nx nodes, we want to determine v1 through phi(nx), which means we now have nx unknowns. And so to solve nx unknowns, we're going to need nx equations. So we'll need one equation for each one of our nodes in our system. So how do we determine what those equations should be? Well, for each interior node, so our interior nodes are nodes 2, 3, 4, and 5, we will use what's called a finite difference equation, which is an approximation of the governing equation itself using a finite difference substitution. So for the heat equation, if our governing equation is now d squared phi dx squared is equal to 0, we have a number of different approximations that we can make for this second derivative. We're going to do one, which is going to use a centered order delta x squared accurate approximation, which allows us to say that d squared phi dx squared is approximately equal to phi I minus 1 minus 2 phi I plus phi I plus 1 divided by delta x squared is equal to 0. Where I've generalized this using our index I corresponding to our spatial index. Now, a critical thing to realize is that our phi values phi I minus 1, phi I, and phi I plus 1 are our unknowns that we're trying to solve for. So we can then write out a couple of these equations. So we have 4 interior nodes corresponding to I equals 2 through 5. So this would give us equations, and you can obviously see that we can pull this dx squared term, multiply it across to the right-hand side, so it's actually going to allow us to drop it. And so this then allows us to say we have equations phi1 minus 2 phi 2 plus phi 3 is equal to 0, phi 2 minus 2 phi 3 plus phi 4 is equal to 0, phi 3 minus 2 phi 4 plus phi 5 is equal to 0, and then phi 4 minus 2 phi 5 plus phi 6 is equal to 0. So those are our 4 equations for the interior nodes in our system. Now for our 2 nodes that are at the edges of our system, we're going to instead use our boundary conditions. So we need a pair of boundary conditions to give us the 2 extra equations we need. So in this case, we would say that phi1 is equal to phi at x equals to 0, for instance, would maybe be something like phi L for our temperature on our left edge, and phi6 then is equal to phi at x equals to big L, so the total length of our domain, which we might say is equal to phi r. And so maybe big L is not ideal, we'll just give this a value of 1. Okay, so these are known temperatures, phi L and phi r are known. And so now we have a system of 6 equations with 6 unknowns that we would need to figure out how to solve for. Well, the most straightforward way of doing this is to convert it into a matrix equation. So we're going to convert this problem into a matrix equation, which means what we're going to do is we're going to say, okay, for a given equation, so let's say we're going to be dealing with that second equation, phi1 minus 2 phi2 plus phi3 was equal to 0, we need to convert this into a row vector times a column vector to give us our left-hand side, and then set the right-hand side in our b vector. And so I'm putting all this in my second row because it corresponds to the equation I would use to solve for my second node. So now we have to come up with the coefficients in this row that when multiplied by our phi vector gives us what we have on the left-hand side. So let's highlight a couple terms. So whatever we put in this space here is going to be multiplied by phi1. Whatever we put in this space here is going to be multiplied by phi2. And whatever we put in the third space would be multiplied by phi3. Fourth space would be phi4, fifth space would be phi5, so on and so forth. But a critical thing that we observe is that there is no phi4, phi5, or phi6 in my equation over here, which allows me then to say that these terms should just be 0. Now I can look at my coefficients in my equation. This would be 1, this would be minus 2, and this would be 1. And those would be then the coefficients that I would put in my corresponding A matrix for that particular row. Now if we go back and look at our equations again, we can see that there's a pattern where for my I equals 2, I have the equation that I just entered into the matrix. For my I equals 3, my terms are just simply shifted to the right by 1 space. I can repeat this process then for I equals 3, 4, and 5, and so that would give me the internal terms 1 minus 2, 1, 1 minus 2, 1, 1 minus 2, 1. And on the right-hand side, I have a value of 0. And that's the case for all 4 of my interior equations. Now we need a pair of boundary conditions, as we said before, and in this case we would say that our phi1 value is simply equal to phi L, and we still need to figure out how to turn this equation into what we would get when we multiply our first row by our phi vector, and then set everything on the right-hand side in our b vector. Well, I only have one term that shows up my phi1 value, and so that means that this term this phi1 corresponds to this spot here. So I would get a coefficient of 1 and then zeros for the rest of the row. My right-hand side would be my phi L value. Similarly, for my last row, I would have zeros everywhere except for my most extreme term on the right edge, which would then be multiplied by phi6, which would then be equal to phi r. So to solve for my unknown temperature profile, I have my coefficient matrix, and my right-hand side vector, which is known. So to solve for phi, my phi vector would be equal to the inverse of my A matrix times my B vector, which in MATLAB is efficiently calculated using the operation A backslash B. So let's talk briefly about boundary conditions. So there are two main boundary conditions that we'll use, although we'll briefly mention a third during the lecture. The first boundary condition is a Dirichlet boundary condition. This is setting the value of the quantity at the boundary itself. And so we had, in our previous example, two Dirichlet boundary conditions where we explicitly said that our phi1 value was equal to phi L. This is a case where we set the wall or boundary temperature. Another example of a Dirichlet boundary condition would be a no-slip boundary condition, where we would say that U is equal to my U wall. Many times this U wall will be 0. We'll have a stationary wall in our system which it satisfies a no-slip boundary, or imposes a no-slip boundary condition in my domain. So this is relatively easy to implement, as we saw in the previous example. The other type of boundary condition that we'll see regularly sets the value of the wall normal gradient of the quantity. So an example of this would be our gradient in the normal direction of our temperature, which, if we have only one direction, maybe it would be something like d phi dx, which we could set equal to some quantity, or we could set it to 0. If we set it to 0, this corresponds to an insulating boundary condition. If we set it to some function which is probably a function of time, this would be imposing a heat flux. The analogy for our momentum equation would be saying something like du dx or du dy was equal to 0, corresponding to a free slip boundary condition. So how would we incorporate a free slip boundary condition or an insulating boundary condition? Well, we have a derivative that we would have to do a finite difference substitution for to give us an equation in terms of our unknown quantities, phi1, phi2, phi3, so on and so forth. Okay?